Okay. All right, we're going to jump right in. If those people that have not turned it in yet, the homework is due in that box by the door over there. Please turn it in now. Actually, in maybe like 5 minutes, go and pick up the box, and then after that, people have the late days. I hate to be a stickler for that, but the reality is people start filtering in kind of 10 minutes late, 15 minutes late, etc. on days homework is due. So we'll just in like 5 minutes go pick up the box, and after that, you're on your own, or you can use 24 more hours after that. All right, so today we're going to keep going through machine learning and talk about a few things. We're going to talk about classification, which is machine learning when you have discrete outputs. We're going to talk about other machine learning algorithms, and we're going to really blow through a lot very quickly here. Without too much detail, you should not be able to implement them after this discussion, but at least having some idea of what these things are. And then we'll talk about, as I said before, what I think is probably the most useful skill when you develop machine learning algorithms, and this is the skill of evaluating and debugging machine learning algorithms. So let's just jump right in. It's going to be a fast lecture today, but hopefully we'll get through this all. And of course the thing isn't working there. All right. So classification. I've mentioned this a little bit before, but essentially it boils down to sometimes we have quantities that aren't real numbers like we have in regression, but which are actually themselves discrete valued things, right? So some common examples are if we want to classify email as being spam or not, that is sort of a binary decision, right? It's either spam or it's not spam. If we have our image or our digit classification task, we want to classify those images as numbers between 0 and 9. And importantly, this is not like a regression task where you're regressing between 0 and 9, because these are really distinct categories. Classifying something as 1.5 doesn't really make sense in a digit classification task. So it turns out we can actually use very similar frameworks as we did for regression for this classification problem. It looks almost identical, the actual math to it, and there's only some very slight differences in how we actually set up things like loss functions. So I'm going to jump into notation. I'll give some examples in a second too, and in fact in the homework the homework that's up now. Oh, I should actually pause for a second. The new homework is due. The homework's due today, but the new homework's also posted today. It has 2 programming assignments, one of which is online and ready to go, and one of which I think should be ready shortly. It's actually a little different. It's a scoreboard assignment rather than a yes/no. You can compete if you want, but we also tell you how to get full credit if you want full credit. You don't have to get the best score to get full credit. So that should be up by today, sometime, hopefully by tonight, 6 p.m. hopefully. Okay, good. So that's up. All the files should be up. Hopefully, I think we've debugged some of the problems, so hopefully go a little bit smoother this time, but we'll see. Okay, so jumping back into the classification, which we're going to do for the homework. That's why it reminded me of this. Just like before, we have some input features, which we're going to call xi, and those are described as vectors in n-dimensional space. Similarly as before, we have an output, but the difference now is that our output, instead of being real valued, takes on values that are either 1 or -1. So like before, we have our xi's. Those are still our n-dimensional vectors. We have yi now, though, which is either -1 or +1. And this is a binary classification task. We'll talk in a little bit how to transform multivariate classification tasks into binary ones. But we're really going to focus on binary for the most part here, because it's actually not very hard to transition from one to the other. So if we have a multi-class classification task, we can transform it actually into many different binary tasks by, say, having a task that says, not is this digit a 0, 1, 2, 3, 4, etc., but is this digit a 0 or not? Similarly, is this digit a 1 or not? So you can create binary tasks this way, though we'll talk about that in a second. Like before, we have model parameters, theta, which are also, at least for linear predictions, these are the same dimension as our feature set, again, our input features again. And we have a hypothesis function. This function that takes inputs in Rn and maps to R. Now this part's important here. We're saying our hypothesis still outputs real valued numbers, even though we're trying to predict something that's binary. What this actually corresponds to is, in some sense, a measure of how confident we are And I'm using the word confidence kind of loosely here, but how confident are we that it's either positive 1 or negative 1? So if our hypothesis H is very positive, it's like 5 or 6, then we're very confident that it actually is plus 1. If it's big negative, we're very confident it's negative 1. And somewhere in the middle, if it's right around 0, we're sort of we're not quite sure what it is. Okay? So this is the sort of the framework we're going to use here. And if we want to actually make a prediction of what this thing is, what some new example is, we would just take the sign of that hypothesis function. Okay? And we'll define the sign as being equal to 0 if this thing is 0. So 0 actually is never right? Because 0 is never plus 1 or minus 1. But it's kind of an edge case. We typically won't get things that are 0. And again, we're going to focus mainly on linear hypothesis classes here. So our hypothesis is theta transpose times x, just the inner product of these two things. If that number is positive, it means we think the digit is the label is positive. If it's negative, we think it's negative. Okay? All right. So now the question is, we have this setting here, and what I want to ask is, do we really need a new loss function? Can we just use least squares with our little labels here, with treating, even though these are binary, can we just treat them as numeric values and apply least squares to this? Right? That seems like a reasonable algorithm. And there's two sort of elements here. One is that you could easily come up with cases where this doesn't work very well. This is one example. So here I'm showing a plot of a classification task. So I have the x-axis are my features again. And the y-axis now is the y value, the outputs. But instead of being real values, these are just either -1 or +1. They have to be one of these two things, right? So what a classifier looks like here, well, what least squares would look like, for example, is something like this. It would look like a line through the data, right? And what you'll notice here is we will classify a example as being positive if this line is above 0 and negative otherwise, right? And in this case, what's happened here is because we use least squares, which kind of tries to fit all the data, we have this point very far over here that is essentially bringing down our estimate, sort of bringing this line down to be more like this, and making it classify this point incorrectly. So it will classify this point here as being negative when it actually is positive. Of course, as you can probably tell, there is a linear classifier here. It's a line that perfectly classifies this data, right? Everywhere this line is positive, the data is positive. Everywhere it's negative, the data is negative. Just perfect on these 5 points, of course. But this kind of implies that maybe least squares isn't quite the right thing to do, right? Because we don't really care if we're way positive, right? Least squares says, if your hypothesis says +5, that means you're, in our nomenclature now, that you're really sure this is a positive example, but least squares would penalize you for that, because it would say the difference between 5 and 1 squared is big, right? Whereas we might want loss functions that don't penalize us like that. So this is kind of the basis of classification, why we typically need methods that are different from just regression. So what loss function should we use? The natural one, the one we would like to use, is just essentially accuracy, or error, rather, the number of mistakes you make, right? So a natural thing to do is say, well, let's find the linear classifier that makes the fewest mistakes, where a mistake is defined as the loss is equal to 1 if the sign, if y, which is 0, which is -1 or 1, doesn't equal the sign of this, and it's 0 otherwise. So we suffer no loss if we get the sign right. We suffer a loss of 1 if we get the sign wrong. Now, I'm going to write it like this. And it's important to know that this thing here is actually the same as this quantity that I'm writing here. So I'm multiplying the label y times my hypothesis. And I'm saying this quantity here is an indicator function. It takes the value 1 if this thing is true, and 0 otherwise. So I'm saying if this thing is less than or equal to 0, take the value 1, take the value 0 otherwise. Okay? And it's important to realize these two things are the same. Does that make sense to everyone, that they are in fact the same? The idea being that if y and h are the same sign, their product will be positive. So they can either both be negative or both be positive. Whereas if they have different signs, their product will be negative. And so what I can do is I can plot now a graph of the loss versus this product here. Okay? This is kind of like the plot of losses versus the difference in values for regression, but for classification, it's really a loss of this product, the product of these two things. So over here, we're sort of really doing really well because we're confident in our prediction and we are the right sign. And over here, we're doing really badly because we think we're confident in our prediction and we're doing badly. Of course, accuracy doesn't really matter, how confident we think we are. It just says if we have the signs wrong, we suffer a loss of 1. Have the signs right, we suffer a loss of 0. So that would just be essentially the error on the data set. Now, the problem, which you can maybe guess, that I'm going to talk about in a second, is that it's really hard to optimize this. So it's really hard to find the classifier that minimizes 0, 1 loss on a set of data points. And that happens kind of obviously here. It happens because this is not a convex function, right? Non-convex functions are hard to optimize. A sum of a lot of these is not going to be convex, and that can be really hard to optimize. In fact, it ends up being NP hard to optimize this. On the homework, you will actually show that this can be solved with a mixed integer program. Those are also NP hard. And you might imagine that is doable. Mixed integer programming is very powerful in that regard. But in terms of solving it kind of in what we think of as an efficient manner, this is really hard. So we're not going to typically do this. We're not going to use this loss function to build our classifiers. We'll often use it to evaluate the performance of our classifier, but we won't use it to build it. So what do we use instead? Well, there are a whole lot of alternatives you can use. And what they all essentially are is some convex function that kind of approximates that function that we saw before, the 0, 1 loss. And that might seem weird, right? Because this seems like it's pretty hard to approximate this with a convex function. Because if you have anything that's 0 down here and 1 anywhere over here, that's almost definitely not convex. Because you could draw a line that does this that will, at some point, the function would be over that line. Right? So these functions are, in some sense, kind of the best things we have to approximate this, though I'll show you their graphs in a second. And they don't really look that much like 0, 1 loss. So we'll use them anyway. A few examples, and maybe actually I'll just go to the next slide, but one example is called hinge loss. This is a loss where you take 1 minus this quantity, the max of that in 0, and that's your loss function. What that looks like, and maybe it's actually better to show what these all actually look like, these look like these things. So here in blue is our 0, 1 loss. And in red here is this hinge loss function. We take 1 minus the product of this thing. That's this line here. We take the max of that in 0. Now, it's important that these losses are intuitively nice in some way, too. And they capture this notion of confidence in our predictions. Because if we are very confident in our prediction, we say we're sort of over here, we predict like a 5, and we're in fact positive, then we have very small loss for almost all these loss functions, right? If we're very confident and we're in fact wrong, we predict -5 and we're actually getting the sign of it wrong, we're going to suffer a very big loss. So these things kind of encode that the more confident we are and make an incorrect prediction, we suffer more penalty. Even though you might not ultimately care about confidence, right? You really want to evaluate your things in terms of errors, but this is kind of how you would actually go about incorporating some notion of confidence into the system. And it turns out that actually a huge number of machine learning algorithms are just a matter of picking different loss functions here. And oftentimes different ways of optimizing the things too, but really different loss functions is what it boils down to a lot of the time. So for example, a support vector machine. Who here has heard of a support vector machine, by the way? OK, a lot of people. Who here has seen it like this, actually? And who here has seen it as in terms of the geometric presentation? Who's seen it like this as a hinge loss plus regularizer? OK, who's seen it in terms of like a maximum margin and classifier? OK, some people have maybe seen it as neither. Anyway, all a support vector machine is it's a regularized minimizer of hinge loss. That's this loss right here, this one that goes up like this. Notice also this one's actually an upper bound on the 0, 1 loss. That has some nice properties as well, actually. But basically, this is sort of a convex approximation, in some sense, to this 0, 1 loss. And that's all an SVM is. It says minimize over our whole data set the sum of Hinge losses plus a regularization term. And that's what a support vector machine is. Now, this problem, unlike least squares, will not have an analytic solution. Right? Least squares is kind of this only case that actually has an analytic solution. This one doesn't. But just like the other problems too, this is a convex problem. This term here is convex. You can see it's convex actually by this term is linear. It's a max of a linear function and 0. That's convex too, and it's the sum of these convex functions. So it's all convex. Okay. No analytic solution, but we could plug it into CVX pi and solve it. And that's not going to be the fastest one also, by the way. For larger problems, there are much better solvers. Methods like, but it actually turns out kind of surprisingly that in a lot of cases, things like gradient descent, kind of the simplest possible optimizer you could think of, actually can work well on these kind of problems. And actually, gradient descent or versions of this are almost state of the art for problems like this, kind of surprisingly. It's actually not differentiable even, so it's not actually even a true gradient. It's called a subgradient, but it's still sort of amazing. This actually works pretty well. All right, so let me show you one example now. And I don't want to get into the actual details of this example. It's an example that sort of I do actually a lot of similar things in my own research here. But what this example is we're trying to take appliances in a home and classify them based upon their power consumption. So in particular, in this plot here, I have 2 refrigerators. And we want to try to figure out when some device turns on in the house, is that refrigerator A or refrigerator B? And the way we can do this is that we can actually describe the different appliances in terms of their power consumption, how much do they sort of consume when they turn on, and how long do they stay on for. And the same 2 fridges, actually different times they turn on and off. This is how a fridge works. It turns on for a little while and then turns off to kind of keep the inside cool. There actually is some variance here. So you can't always tell perfectly, but you can get a pretty good sense about if it's this one or this one. And what and the input feature here, the xi would be a vector in R3 that would include this one, the power increase, that's this axis, the event duration, that's that axis, and then a constant term 1. And it's important to visualize classification tasks like this. These 2 axes here are both the inputs now. And the output, the y, actually I'm not plotting as an axis here. I'm plotting y just in terms of, is it an x or is it a red x or a blue circle? Right? So you just kind of think of this as the actual y-axis would be a 3rd dimension that comes out here, where these ones would all be raised up and these ones would be kind of sunk in to the board here. But we don't need that because we can just show them in their colors. So that sort of is as good a way of doing that. And it gives us one more axis to look at in terms of visualizing the actual features. OK? All right, so this is the classification task we have here. And I guess as I said, the details aren't that important here. Here's one class, here's another class. We want to classify these things as being red or blue. And here is the decision boundary given to us by a linear support vector machine. So a support vector machine with a linear hypothesis function in these 2 features. OK, so it's important to sort of get this visualization right here. What's really happening is that we're taking this data, and our hypothesis function is a hyperplane in 3D space, right? Our hypothesis says you take these 2 inputs, you add a constant term, and that becomes your output. The output would then be kind of in this axis here. And when I'm showing this boundary is the location where that hyperplane crosses the z-axis. All right, so it sort of looks like this, something like this, coming out here and then going into the wall there. And then what I'm showing is the place where that crosses the axis. And that's an important line because what that means is that everything on this side of the line, this hypothesis is positive, and on this side of the line is negative. So this line is the classifier boundary that separates out everything here is positive, everything here is negative. It's not doing what regression does here, which is try to sort of fit a line like this to the data. What it's really doing is trying to separate the data with this line. As I said, that's the boundary you get from a support vector machine with these two features plus a constant term. Now there's one more very common classification algorithm which we're going to talk about here. I'll mention a whole bunch later too, but in a lot less detail. And that's logistic regression. Logistic regression is actually the exact same form as vector machine. It's just that instead of the hinge loss, we have something called logistic loss here. And that is the log of 1 plus e to the negative thing here. And that actually looks not that unlike hinge loss. I'm going to flip a few slides back and go to my plot of all these loss functions. That is this green one here. It actually also approaches a straight line as it gets further and further negative, and it approaches 0 as you go over here. The difference, though, is this one's actually kind of more of a much smoother function. Okay, so basically, this one here is non-differentiable. The hinge loss is non-differentiable at 1, whereas logistic loss is differentiable everywhere. And so because of that, it has some nicer optimization properties. Now, let's get back to this. Now, one big thing, which I'm really not talking about at all here, are probabilities. It might be actually sacrilege to talk about machine learning without ever mentioning any probability, any sort of notion of probability. But I think you can. I think we can talk about it just in terms of loss functions and minimizing loss functions. But it should be said that logistic regression really is important largely because it not only has this sort of nice optimization form, but it also has a probabilistic interpretation. In particular, under certain assumptions, you can interpret this term here, which is actually kind of related to this guy here. This term here, 1 over 1 plus the exponent of this thing, you can interpret that as the probability that y is positive given this. This number will be between 0 and 1, and you can interpret it as this probability. Now, we're not going to focus on probabilistic interpretations at all in this set of lectures. I think you can talk about it without probability, so we're going to do that. But you should at least know that logistic regression has that interpretation. So again, as I was saying, this is a optimization problem. It is convex. This follows the rules of convexity, actually. You can check to make sure that is true. Actually, I think I made a mistake. Did I make a mistake here? I think I might have had a 1 minus that. Oops. No, I think I might be right. OK. This ends up being a convex function, right? Because it's a log sum x function or something like that, a log sum x function. So it is convex. But it's not, again, much like really any problem except least squares. You can't analytically solve for the thetas that minimize this whole thing. Okay? Even when this h here is a linear function. So just like with support vector machine, we cannot actually analytically solve for the thetas that optimize that. So instead, what's very common, because this is a smooth function, is that we use Newton's method. I talked about Newton's method very briefly in the optimization lecture. What it boils down to is Newton's method is essentially a root-finding algorithm applied to trying to find a place where the gradient of this function is 0. Remember, when the gradient of that function, the gradient here is, and I'll have some more notation in other slides, but it also is in the optimization lecture. When the gradient of this function is 0, that means we are at an optimal location for theta. Right? That means the gradient meaning the derivative of this thing with respect to each element of theta. When all of those are 0, because this is a convex problem, that is the optimal solution to theta. Now, in this case, we can't find that by just writing down an equation and say solving for theta. Actually, can't do that. But you can apply Newton's method to iteratively find a location where the gradient of this thing is 0. And in practice, it takes maybe on the order of 10 iterations to do this. You have to repeat this process 10 times, and then you'll find something that is 0 to numerical precision. You're sort of happy. We solved it as far as we can on a computer. So this next slide, don't be too daunted. It just has the equations for the gradient of this and the Hessian of this. That's what you need to compute Newton's method really it's just more definitional than anything else. So here is how you solve logistic regression. We have our objective function here, and I'm writing it as a function of theta, because theta is the only thing we're really trying to optimize over. And I've replaced the h there with the actual linear term. So I put in phi. Sorry, ignore that phi. Sometimes you write phi to denote features of x, but just we've been using just differentiation x for this class. Here I have it again, too. Sorry about that. OK, so the gradient and Hessian are given by the following. The gradient of f. Remember, the gradient of f is a vector. Gradient to theta of f of theta. That is a vector, and the ith element is just equal to the partial derivative of f of theta with respect to theta I. OK? And all I'm doing here is I'm actually just telling you, and you don't have to. I'll get rid of these thetas. I'll post a revised version just to, sorry, get rid of these phis in case anyone's confused by that. But I'm just telling you that if you take this function, do math, basically run calculus on each one individually, sort of use the chain rule, all these kind of things to get what that is, and then look at it in vector form, the entire gradient. You can write it like this. You can write it like x transpose z of y, where z is a diagonal matrix with these entries. And actually, those are the probabilities we talked about last time, so, or something close to those. So just a fact. You can try to prove it if you want. It's just basic calculus. You can do it element by element and confirm this is in fact the case. But you don't have to for this course. I'm just telling you. Similarly, I'm telling you the Hessian is this form. The same matrix Z, you have x transpose z times I minus z times x plus 2 lambda I. By the way, these two terms here, this 2 lambda theta and 2 lambda I, those are the gradient and Hessian of that regularization term only, of only that 2 norm term. And these ones here are the gradient and Hessian of that log term. Once you have this, and you don't have to just trust me that these are in fact the correct gradient and Hessian, you can solve for theta by just repeating these updates. You form these two matrices, then you set theta equal to theta minus the Hessian inverse times the gradient. You just repeat that process. That's Newton's method, which we covered before. But you just iterate that process. And you can derive it all. You'll see that it all works. But for here, I'll just tell you that this works. You can use this in the homework if you want to. This is an example that will get you full credit on the homework if you want to. But there are other ways to do it as well. So I'm putting this here mainly as a reference, so you can go back and implement it if you want to. Details here we're not really covering. Big picture is we have some regularized loss minimization problem where we've chosen this logistic function as our loss function because it looks kind of like 0-1 loss, and it maybe has a probabilistic interpretation too. And if you want to minimize this, you just follow this procedure right here. Iterate like this until, basically until this term, until the gradient, until the norm of that gradient is less than like 10 to the negative 10 or something like that. Something really small. And it'll become really small really fast here. OK, moving right along. It's going to be a fast lecture, as I said. Here's the classification boundary you get from logistic regression. It is not that dissimilar to what you get from a support vector machine. Another fact of machine learning is that oftentimes a lot of algorithms will give you very similar results. I mentioned this with regression, right? I showed you the absolute loss function, the squared loss function, this deadband loss function. And they all look kind of similar on this problem that I had before. But here, we have something that often happens again, as in often a lot of these algorithms will give you very similar results. Now, you can always come up with cases where one will perform very differently than another. But on real problems, just in practice, it ends up being the case that the differences aren't that huge here. So Oftentimes, you want to spend more time, say, developing new features rather than just running a million different machine learning algorithms. There is some limits to that, certainly, and sometimes a certain algorithm will do much better than others. But often, trying out a couple is kind of good enough. I think this took about 10 iterations of Newton's method to actually converge, and the gradient here is 0 to numerical precision. All right, are there any questions now? Maybe I'll stop once or twice and ask that. Okay, everyone could just implement that, no problem. It'd be easy. You actually could, right? And you can if you want to for the homework. But it's there for reference more than anything else. So you can go back and implement it if you want to. Okay, let me mention two more things now. The first, I mentioned this a little bit before. There are cases where you have more than one classification, or more than two, rather, discrete outputs. Right? So rather than saying it's yes or no answer, you have yes, no, or something else. It's a bad example, because usually those are the only two options. But you have a digit, right? And the digit is either 0, 1, 2, 3, up to 9. It's not a yes or no question. So it turns out that you can actually solve those problems using binary classification. This is a very common approach. It's called sometimes one versus all, because you're building a binary classifier to detect each individual class versus all the rest. The idea is you have our y's, and y's now are in some set, 0 to, I should probably have it be 1 to k, not 0 to k. But they're in some set 1 to k, say. And we're going to create a new set of y's that are binary for each of the different possible labels. Right? And I'm calling these y hat superscript j, which is equal to 1 if this label equals j, and -1 otherwise. So these labels here are an indicator of, is the ith example, does it have label j? Okay? I'm trying to be precise with this notation here, but it's really a simple idea. Right? You just take all your things and you build a new task that says, rather than is this 0, 1, or 2, is it 0 or not? Is it 1 or not? And is it 2 or not? Now, as you might imagine, you can get into some trouble here, right? Because you could have an example where they all tell you, yes, it's 0, and yes, it's 1, and yes, it's 2. And so what do you do then? Well, first of all, you fit your parameters to each, for each binary classification task, you fit a set of parameters on that task. There should be a superscript j here as well. So you fit parameters for each of these tasks. You solve a binary classification problem. And then when you have a new input, you classify it according to whichever hypothesis is most certain on that example. This is sort of one of the benefits of using hypotheses that are continuous valued rather than just discrete. They can also all give you a confidence level, essentially. And so you just look at all these h of all the thetas and just pick the one that's the biggest. And that's the class. Okay, so it's sort of what you would think to do anyway. If you had a binary classifier that was really good and wanted to apply it to multi-class setting, just build up k different classification tasks, k different binary classification tasks, and see what the outputs are. Pick the output that you're most confident in. Does that make sense to everyone, what we're doing here? Okay. There are some variations, like building tasks for each pair of labels and doing all n choose 2 of those. But we're not going to really, or k choose 2 rather. But those are a little fancier. They perform better sometimes, sometimes not. We're just going to think about this. Yeah. Yeah. You could certainly come up with sort of an actual procedure for saying, classify this as either one of these first k over 2 labels and the second k over 2 labels. And then for each one, you build another tree. You can definitely do that too. Actually, this is another common thing. You can also use what are called error correcting codes to try to predict different binary values of an error correcting code for these things. There's a lot of different variations. This is usually the simplest one. The other ones can actually be more computationally efficient if you have a lot of classes. But this is a pretty simple one that works well for a reasonable number of classes. All right, and secondly, the nonlinear case. So what I covered so far were these linear hypothesis classes, right? Our hypothesis class was h theta of x equals theta transpose times x, right? And the only point I want to make here, because it's exactly the same as the point we had in regression, is that this, despite looking pretty simple, is actually a very powerful class of hypotheses. And it derives its power from the fact that you can choose whatever features you want as your input, including nonlinear features of sort of the natural input. So what I'm showing here now is actually a slightly different task where we're trying to classify a fridge versus everything else. So the other fridge is here, but there's also other stuff all around it. And what I'm doing here is I'm actually showing you the classification boundary of a support vector machine that uses nonlinear features of the inputs. So remember, you can take things like polynomial powers of the input, stuff like this, to get a nonlinear regression line. You can do the same thing for classification. And in classification, what a nonlinear set of features look like is it looks like things, decision boundaries that are not lines anymore. Right? Because again, what's really happening here is you're fitting a function, sort of a 3D function, to this space, where the things in red are positives. They're kind of coming out. And so basically, this function is kind of curved here and positive in the region where it's red. And it's negative. It's behind the slide here in the regions where it's blue. But just like you can get nonlinear functions out of nonlinear features in regression while still using things that are linear in your parameters, you can do the same thing for classification. And so you can classify things that are funny shaped, things where your 2D plot would be some interesting combination of different patterns here. You can still often classify that using a linear classifier. The caveat is you have to use nonlinear features. Okay. So that is all for classification. Any questions now? We have a lot coming up in this next one that I'm going to try to get through quickly. All right, let me talk now about other machine learning algorithms. This is going to be, as I say, a whirlwind tour. Linear classifiers are really, they're fantastic. They have a huge amount of power. If we choose the features right, they can be incredibly powerful. But they aren't all that exists. There are other algorithms that use nonlinear hypothesis classes that, in all honesty, can sometimes do a lot better than linear methods. Or at least take less work, less tuning than a linear method will take. So in particular, many other algorithms will use different hypothesis classes or different loss functions, possibly non-convex loss functions, or maybe different routines for optimizing these loss functions. And those three things, I guess these two things plus the different optimization, really does get at enumerating almost all the machine learning algorithms that there are. They almost all can be interpreted in this manner. So let's list a few. One thing you may have heard of is a class of methods called kernel methods. These are actually linear methods. The hypothesis class here is our hypothesis on x is the sum from I equals 1 to m of theta I, our parameters, times some function here, k, of x and xi. The xi's here are all the data we have. Remember, we have m different examples in our training set. And so we take each of those examples. We compute some function called the kernel function And this kernel function kind of intuitively, it measures similarity between these 2 points. So it's big if they're similar. It's small if they're not similar. Multiplies those all by some weights, theta, and that's your hypothesis. Now, you can interpret this in a lot of ways. And for certain k functions here, you can actually interpret this as working in a higher dimensional feature space without ever forming those features explicitly. And don't worry about that, because we're not going to cover that. But if you see this presented in a machine learning course, you will probably see that interpretation of them. And there are other much more sort of functional analysis interpretations as well about things like inner product spaces and these sort of fun other elements. But this is all it really is from an implementation standpoint. This is all it is. And in fact, this is a linear function too, right? This is also a linear hypothesis space because it's linear in our parameters theta. What that means is we can use all the exact same algorithms as we did before to optimize them. So we can use convex methods. If it's least squares, we can use just analytic solutions, etc. And in fact, it turns out that really support vector machines became popular. I mean, just the loss function isn't that different, right? Sort of similar to what we had before. They became popular largely because they were integrated with kernels and kernel methods, and they happen to have properties that make them very well suited to kernels. Now, one important point here is that here, theta is now a vector in Rm. Remember, n was the dimension of our feature space, and m was the number of examples we had. Before, we always talked about theta being the size of our features. And here we're talking about theta being m-dimensional. There has to be one for each example. This means two things. First of all, it means that we may have a lot more parameters to fit, potentially. So things like overfitting might become more relevant, and we need to be careful about regularization. But kind of more importantly, it also means that to compute this function here, we need to keep around all our examples. All our training data, we have to kind of keep it with us. Because to compute a hypothesis, we have to actually compute some of this kernel between our x's and our examples. Now, this is in contrast to normal linear hypothesis classes, where once we've trained it, we have our parameters theta, and we can throw out all the data, right? Because we just take theta times itself times that feature vector, and that's our prediction. Here we can't do that. Here we actually have to keep around all our data in order to make predictions on new examples. And this is what's called a non-parametric approach. I won't get into it's sort of a horrible term because there still are parameters, but these are called, essentially it means the parameters are not fixed. There's a growing number of parameters because as you get more data, you need more parameters. Another method in this same class, a non-parametric method, is what are called nearest neighbor methods. These are actually conceptually simpler. The idea is you have some new example you haven't seen before, a new set of input features. You find the example in your data set that it's closest to, and just predict the label of that old example. This is also non-parametric because you have to keep around everything you've seen. But one thing that's nice about this is that other than that, it really requires no training, right? There's no real training phase to this. It just requires that you just keep all your data around. The only hard part is when you have a new example you want to classify or do regression on, you need to compare it to all the examples you've seen so far, which can be very computationally expensive as you go. And there are also variants that don't just take the closest neighbor, but actually average over multiple neighbors, called k-nearest neighbor methods. Okay, but this is a very popular approach because it's very simple. In fact, quite a bit simpler than kernel methods, even though kernel methods are also non-parametric. Okay, moving right along. Neural networks. Who here's heard of neural networks? It's a great name, right? Fantastic, fantastic marketing done. Neural networks are fundamentally non-linear hypothesis classes. That's where they differ from linear methods. I am showing one example here of a neural network function. So let me describe this. The parameter space that we have here is actually consists of two separate parameters, a matrix theta1 and a vector theta2. The way we produce outputs here is we take our matrix theta times x and apply this function sigma. Sigma, in some cases, is what's here. Sigma, I'm calling the sigmoid function. The function that kind of looks like this. Doesn't really matter what it looks like, actually. So here is 0. It's negative, and then 0.5 at 0 and goes to 1 over here. Sorry, it's not ever negative. For negative inputs, it's it's 0 and kind of smoothly becomes 1 like this. The important point about this function, for this case of a neural network, is that this function is a nonlinear function. It's a nonlinear transformation of the input. So if we take this, apply some matrix to it, everything's still linear now, but we apply some sigmoid function that is a fundamentally nonlinear transformation of the data. We apply another matrix, say, and then we take a sigmoid again, and that gives us our output. So one way of thinking, people will often draw it like this, as these sort of networks here, where you have your inputs, you multiply them by this thing, and then apply a sigmoid function to get this set of parameters here. This is this guy right here. These z's here would be the actual sigmoid of theta1 times x. And then you do this thing again to get your y output. And I guess I think by this definition, actually, y here should be either 0 or 1, not negative 1 and 1, because the sigmoid maps between 0 and 1. You can come up with one that also, just by multiplying it by 2 and subtracting 1, you can get one that goes from negative 1 to 1. And this in particular is called a two-layer neural network, because there's two layers to it. There's this first layer here and the second layer here. There's two sort of nonlinear transformations you make. And it turns out that if you have enough of these things here, and these are called hidden units because they really have no bearing on the original problem. Right? You never observe what these things should be. You're just kind of using them as a way of representing arbitrary nonlinear functions. And the more you have of these, you can actually start to recover extremely powerful categories of approximation functions. You can approximate actually any function you want with a two-layer neural network. Or a one hidden layer neural network, that would be the better way of calling it. People sometimes will call it 3 or 2. There's some notation there, what you call a layer, but we'll call it here 2-layer. Okay, so now I'm not getting into actually sort of the details here at all, but the important point is that what a neural network is it takes nonlinear functions of the input and maps those to the output. And it cannot be recreated, or it is fundamentally a different representation than just linear hypothesis classes. One thing to keep in mind is that even though this is of course now non-convex, I should say, right? This is an incredibly non-convex function. There are all sorts of local optima. People spend a very, very long time coming up with good ways of optimizing these things. However, one of the simplest, again, kind of works very, very well here. In particular, gradient descent, which in the case of a neural network goes by the name of backpropagation. That's really a way of computing the gradients. This works extremely well in practice. And so people apply these backprop algorithms to optimize, to find the parameters, those theta matrices and vectors, that make the outputs, for a training set, make you produce the outputs for the given inputs. These are also becoming, have seen a amazing resurgence in popularity in the last, I would say, little less than 10 years. Due to a lot of factors. There have been some sort of tweaks to the algorithms. The algorithms actually are not that different from what they were in the 80s, when these first kind of really gained prevalence. What's really happened, I think, is that we've just grown in computation so much. There is so much more computational power that these things are becoming incredibly relevant again. They have huge representational power. They have simple algorithms. That means they can process a lot of data and capture very complex functions. And that kind of gets at a lot of what we want in machine learning these days, right? Lots of data, complex functions, big optimization problems. And so I think for those reasons, these have become really popular. There have been huge successes in things like speech recognition. These things, or particular deep networks, so those are things with many different layers, more than just 2 layers. Those have really caused a sort of a small revolution in how we do machine learning for things like speech or image recognition. If you want to know more about this, there are classes, I think, there are starting to be now finally classes that really focus on neural networks and deep learning architectures. Okay, jumping right along. This is an AI class, so I would be remiss to not ever mention decision trees. Decision trees are another hypothesis class that essentially will partition the space of inputs with a set of, you can think of them as kind of cuts through the space. So we take our input x, and we find somehow a split. We say, if x is greater than 2, we take this branch. If it's less than 2, we take this. Greater than or equal to 2, we take this branch. Less than 2, we take that branch. If we get here, we say we're going to output -1. These leaves can also, by the way, they can have, themselves, they could have linear classifiers on them or linear regressors on them. But it's actually a little more common to just have a fixed class label at the leaves. Then sometimes we split more. So we say, OK, now if you look at x1, you have these alternatives here. What this looks like is kind of a partitioning of the space along its boundaries. So if we had something like x1 and x2, these being the 2 dimensions of x now, not being different examples in our data set, you'll have to forgive me for switching back and forth to those. That's just sort of the reality of notation. What it will do is it will say, so first x2 be greater than 0. So if this or greater than or equal to 2, so this whole space, we say -1 in this entire space here. Otherwise, we split on something being greater than or equal to -3. So we have this split here. Here we say, if it's greater than that, we say this is +1. Otherwise, we say it's -1. Okay, so this is a plot, essentially, of the function that this decision tree produces. The parameters of these things are the splitting points and the actual structure of the tree itself. Those kind of are the parameters, right, of this model. And the way we learn those, there's a lot of ways you can learn them, by the way. And for a long time, machine learning talked about papers. There's a ton of work on different criteria for how you form these things. But essentially, what people do in practice is they use more or less greedy methods to pick the splits that seem to separate the data set best right now, and then they sort of move on iteratively. So if we have some data set where all these examples here are negative, and these ones here are all positive or negative, we might split here first, because that kind of separates out all the negative ones up here first. That looks like a good split. Now, when I say separate it, to best separate it, that's a tricky sort of criteria what I mean there. They actually use kind of involved procedures for doing this. They aren't that involved. They use a little bit more complex procedures there to make this tractable. But that's the basic idea. All right. Finally, last one I think we're talking about is ensemble methods. Ensemble methods they're exactly what they sound like. Rather than you make a hypothesis class, rather than just having one classifier, you have a bunch of classifiers, and your final hypothesis is some combination of the other ones. All right, so the notation I'm using here is we have k different classifiers, which I'm calling hi, from I equals 1 to k. You would now, of course, also have parameters for each of these base classifiers. They would have their own set of parameters, but I'm kind of ignoring that here. I'm just saying that our final hypothesis is essentially a weighted vote of what these classifiers are all predict. And it's a little bit more common. You notice I'm actually taking the sign of the prediction there. It's a little bit more common to actually do that, to look at the sign of the prediction that they all make, not their individual confidences, but it's their sign, and take a weighted vote of those, where thetas here are the weights. That's the most common way of doing this. You could, of course, also just take a weighted combination of the actual confidences there too, but for sort of various reasons, people tend to take the sign and look at the actual predictions rather than the hypothesis outputs of the different classifiers themselves. So this is typically done for classification, not for regression, but you can do it for regression too. You certainly can, and many people do. I shouldn't even say it's typically done for classification. It's done for both of them, in which case you would not have a sign here. Some popular examples of this, there are two very famous ones. They're called random forests and boosting. Random forests, it's usually the base classifiers are decision trees, hence the forest name, because lots of trees are a forest. And the idea is you create lots of a decision tree based upon different subsets of training data, and just take usually just a majority vote. That's all it is. And these work amazingly well for a sort of simple algorithm. Boosting is a bit more involved. You actually will there iteratively weight your examples based upon how well past classifiers have done them, have classified them, and then build a new classifier based upon this reweighted set of examples. But it's actually quite simple. What you do essentially is every iteration you weight your example such that the last classifier gets 50% accuracy on the new reweighted samples. And you just repeat this process. Coming up, it's not quite that because you have to come up with different weights here, et cetera, but it's essentially that process. Probably, if you were to sort of put money on any single algorithm doing the best, this is probably boosted decision trees were probably your best bet for a long time. Maybe they're being beaten now by these more advanced neural networks, but these are really, really good, and they still are really good for a long time. Having said that, I will almost never use these first. I will always use linear classifier first because they're much simpler to implement or test, and they're also much simpler to debug, which we'll get to in a second. It's just much simpler to visualize what's going on with linear classifiers. So these are great, though. OK, one last thing before I move on to debugging, and that is unsupervised learning. So this is going to be very quick again. But the idea here is that in all the examples I've talked about so far, we've had a setting where we have input features as well as an output. And the goal of our machine learning task is to predict the output from those inputs. There is another class of machine learning methods called unsupervised algorithms where you just get inputs. You don't get an output. And the goal now is to do something, right? Basically, the goal is to discover some sort of structure in that input, whatever that may mean. Now, it's not often presented like this, but it turns out you can frame a lot of unsupervised methods in the exact same way as a supervised case, with two little differences. We need a new kind of hypothesis class and loss function, right? Because the hypotheses now can't try to output a prediction of the label. We don't have labels. What we're going to do instead is have hypotheses that output inputs, or something that's the same size as the input. So our hypothesis class takes inputs in Rn and outputs some value in Rn. And the loss function is usually some notion of how different our hypothesis is from the true input on all our, and again, you would sum this over all your data. This seems very odd, right? Because we could always have this be an identity function, and we would get perfect accuracy. Now, of course, what stops that is that we will restrict our class of functions such that they cannot do that. They have to, in some sense, make some sort of modifications of the input. And after those modifications, we want to try to get out something that is as close to our original inputs as possible. Okay, and this is actually a way, it's not usually, again, the way you think of it the first time you see it, but this is actually a way of framing most unsupervised learning algorithms. An example of this would be something called k-means. So k-means, intuitively, it looks at the inputs and picks k different centers of your data such that each point is hopefully close to one of those centers. So it kind of finds, like these sort of central points in your data such that everything is close to one of them. It'll also assign each point in your input to one of those centers, which acts as a clustering of your input points. But the idea is you have these centers, and your hypothesis just says, I'm going to pick the center. I'm going to make my prediction of what my example is here based on whatever center is closest to. So I'm going to always output one of these centers, one of these mu's, which are the same size as your input dimension. I'm going to output whichever one is closest to the input of my hypothesis function. That's all k-means does. And now the problem is to find the means that minimize the squared loss for this hypothesis function, namely the sum over all I of this minus that, which is just really finding the means that minimize this distance here. I'm using a lot of these argmin and argmax. I guess I don't use argmax. I use argmin here. Argmin just means if you look at all the mu, so this function expression here, for example, would mean if I look at all the mu i's, I have k of those. I have k different mu i's. I look over all I and find the one that minimizes this expression. That's the one that has the mean closest, or that is closest to x. And then I select that index. So I'm taking that mu I. That's all I'm saying here. Now, this here, turns out, is not a convex problem. This argmin here makes it non-convex. But you can solve it with a form of alternating minimization, where you first assign all the examples to their closest mean, and then reassign the means as the average of all the points that are assigned to it. It's a very simple algorithm, and it approximately minimizes this objective here. The other sort of canonical unsupervised learning method is called principal component analysis. What this does is this has a hypothesis class where h theta of x equals the product of two matrices times x. Where here, theta 1 is a fat matrix, and theta 2 is a skinny matrix. In particular, theta 1 has k columns. Oops, did I write that backwards? Yeah, sorry, I wrote that backwards there. This one is skinny. This is skinny. This one is fat. Right, so theta 1 has k columns and n rows. N is the dimension of our input, where k is much smaller than n. So it's a skinny matrix. And we want to minimize just the sum of the differences between this transformation applied to it and x. There's some issues of centering here and stuff like this, which I'm not alluding to here, but you may have to center the data depending on sort of basically subtract off the mean depending on sort of your precise setup here. This is sort of conceptually what it's doing, though. This is all it is. So it's doing loss minimization, where it's trying to minimize this reconstruction loss, where this is our hypothesis class. And the idea here is that because this thing is k-dimensional, theta 2 times x is k-dimensional, that means we only have k elements, k dimensions, to kind of capture what's important about x. Because this is sort of a smaller term here than the full x, so we can't really have this be the identity because this is a smaller term, right? So this is a smaller term than x, so we want this term, whatever it is, to kind of capture the most important qualities of x, such that we can reconstruct x by this other matrix here. And for this reason, it's called also sometimes a dimensionality reduction algorithm, because this quantity, x2 times x, sorry, theta 2 times x, you can think of as a reduced dimension representation of x. It captures the same quality of x without actually being as high dimensional as the full x. Now, this here is not a convex problem. It has a product of two matrices and trying to optimize over both of them that is almost never going to be convex. It turns out that this is one of the one and only problems not just PCA, but problems based upon the same structure, that you actually can solve despite the fact that it's not convex. And you can solve it with what's called an eigenvalue decomposition. We're not going to worry about that at all. A lot of toolkits will have the sort of the ability to do this very, very quickly, so we're not going to worry about how you do it. But essentially, just know that non-convex, yet you can still solve it with an eigenvalue decomposition. All right, and that brings us to the end of our whirlwind tour of ML algorithms. One final point. The good news of all of this is you do not need to know how to implement all of these things. There are libraries available that can do this. For Python, a very good one is called scikit.learn. It's actually, it's fine. I don't want to advertise it over other ones. There are lots of good ones. That's one that's sort of pretty popular. But also, a word of caution is to be careful. A lot of damage can be done by just indiscriminately applying whatever algorithm you have. Not really damage, but a lot of waste of time can occur if you indiscriminately apply every single algorithm in a package like this without having any idea of what they are doing. And you pick the best one because you think it does best in this other thing, but you don't really evaluate it correctly. And so all sorts of problems can ensue from that. So use code, but be careful. And read up, take a machine learning course, figure out what they're doing before you go too wild, applying every algorithm you can to every problem. And with that, I want to get to the last point here, which, as I said, is the most important point of machine learning. This is how you evaluate and debug algorithms. Any questions? We have 12 minutes left, so hopefully I'll be able to get through all this. All right, so first of all, evaluating them. There's two different things kind of in a way, right? Evaluating and debugging, though they're related. How do we know if our method is good or not? So suppose you develop some machine learning method for your favorite problem, and you want to know if it works well, right? That's something you might want to know. The standard thing to do is to divide your data. You have all your data. You divide it up into a training set and a testing set. You train the system on the testing set. Sorry, you train the system on the training set and test it on the testing set. Right? Imagine that. Now, the important point I want to make is that this sounds very similar to what I talked about when we talked about validation sets versus training sets. The testing set is not the same as the validation set. This is very important. This is a very common mistake people make when developing machine learning methods, and it is not a valid way of doing things. So let me describe to you the right way of evaluating machine learning algorithm. 5 steps here, and one's optional, so it shouldn't be that hard to get right. So first thing you do, you take all your data, and you break it into a training set and a testing set. So this is all your data. You do this randomly, too, because you don't want the order of things to matter. Unless the order really does matter, like maybe you want later data to be in testing and earlier to be in training. That's fine, but usually you just do it randomly. And say you take 30% as your testing set, and the other 70% as your training set. OK, now a very common thing to do is say, OK, this is what I'm good. I'm going to train my method on this. I'm going to pick a decision tree or a neural network or whatever on this. I'll tune my regularization to get the best results I can, looking at how they do in the test set. Never, of course, looking at how they do in training error, but just looking at how they do in the test set. I'm going to keep doing that, and I'm going to report now the best test error I get over all the sort of things I've tried out thus far. I never trained on this data here. I never used it to solve an optimization problem. But at the same time, this is not right. Can anyone see why this is wrong? Yeah. Exactly. You're not minimizing any specific optimization problem from your test data, but you effectively are. You're choosing all these extra features, which algorithm you use, which regularization parameters you use. You're choosing all of this based upon your test set. And then you're just reporting the best result. You are effectively reporting something that's very similar to training error. The right thing to do is the following. You take your other training data, your whole training data, and you divide that again into the validation set and sort of second training set, the real training set. Say again, doing 70-30. You do your optimization based upon this here. And you do all your sort of selection of which algorithm you use, what regularization parameters you use, how many features you use. You do all that based on performance in the validation set. Then, and only then, you maybe optionally, so you can get all this data, right? So you use all the data, you take your final parameters, you train on all this training data, and you evaluate your performance on the testing set. Do that one time and only one time. And if it's good results, you get a paper. If it's bad results, you put the research away forever and never touch it again, because clearly you could never bias your results that way. That is the right way to do things, right? Now, of course, that's not what happens in practice. In practice, you sort of test, you sort of peek behind the curtain occasionally, right, and sort of see how you're doing. Then you, oh no, you never do that methodically, but you sometimes peek and you see how you're doing. That all will bias your results, right? That will all make it so that you are picking, just even conceptually, you're picking methods and algorithms based upon how you're doing on this testing set. So you can't do that. That being said, sometimes there's just, you can't really avoid it. Or maybe actually what's better to do is you do this many times, but every time you sort of try a test set, you get brand new data for your test set. And you throw away everything else. That would actually be fine to do too, right? If you were sort of to recreate this every time you wanted to do a test on your test set. And you can't do that very often, because whenever you do that, you have to spend all the time collecting more data again afterwards. So there are big pitfalls here. This is the correct thing to do, but just be aware that it's correct and almost no one does it perfectly. We all strive to, but it's sometimes hard. So now, the single most important thing. This is, and I'm taking this sort of, as I said last time, I'm taking some of these notes from Andrew Ng, who has a very great lecture on the same thing. Here's the problem that most people come across when they are new machine learning students. Develop some system, train logistic regression, or any other classifier you want on a problem. You do this whole evaluation, you tune it, and what you find is it's not good enough. It doesn't work. What should you do? And say, so just in this case, we're saying that both the training and testing error are just too high. What should you do? Should you add more features, collect more data, try a different method, try a neural network, use a higher or lower regression parameter? You could do all those things, right? And it's very common for people to just essentially try all of them. We'll try everything and see what works. And that can work sometimes, but you will waste a lot of time doing it. Quick quiz here. What should you do? We have only very little time, so what should you do? You train the classifier with regularized logistic regression. Training and testing errors are both higher than you thought. Which should you do? Should you add more features? I just pick quickly here because we haven't gone over this in detail, but just pick what you think would be the good thing. Add more features, remove features, collect more data, try on neural network, increase regularization or decrease regularization. It's more. You can do more than one of them. Select all the things you think you should do. And because we're almost out of time here, and I have a few slides after this, we'll end at 47. Or maybe 46 even, if people can get it quickly. No, 47. I don't want to be crazy. Oops, it's showing the results. Dang it. Hide results. You aren't seeing results, right? OK, 5 votes so far. All right, 10 more seconds, so get your final choices in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, anyone still desperately doing it? All right. Okay. Oops. Need to show the results. All right. So, a lot of uncertainty, right? Which is right. This one won't count for too much because we haven't really told you the answers yet. Okay. So, what should you do? The fundamental problem here: training and testing error are both high. They are both too high. Your training error, you are trying explicitly to try to minimize that. Maybe not quite, because you're actually minimizing a surrogate to your training error. But logistic loss and things like this are actually pretty reasonable surrogates. So you're trying to minimize your training error. What this is saying is that even the absolute minimum of your training error is still not good enough. Your hypothesis class, therefore, is just not expressive enough. Add more features, that's good. That'll make that you should do. That would be a good option, at least. Good one. Removing features, that won't really help you. Because even with all your complexity of your class, you're actually not doing very well yet. And so taking things away won't actually help you. Yeah? No, it really shouldn't. Because your training error is too high. And if your training error is too high, it means that you are not able to even, on the data that you are trying to fit explicitly with all your parameters, you still can't do a very good job of fitting them. So basically what it means is that reducing the dimension is not going to help you here. Collecting more data also will not help you here. You should not do this. This would be a waste of time. Doesn't matter how, and actually maybe I'll show the graph in a second that maybe describes some of this a little bit more, but a neural network, that'd be great. Yeah, neural networks are more expressive function classes than logistic regression. You may benefit. Increased regularization, that will not help you. That is going to make your function basically penalize you more. It's going to increase training error more. It won't help. Decreasing it, yes, this will help. Okay, so I mean, this just goes to show this is the kind of things you should think about when you have to know what to do. And I'm going to show one more thing here. What I'm going to show is that can be very hard to realize at first, right? Admittedly, it can be hard to know what to do. Here is a very good diagnostic you can run that can tell you what to do. Okay, and I should say, almost all my time I spend writing machine learning code, I spend writing diagnostics, not actually developing new algorithms. Or developing new algorithms, but writing diagnostics to diagnose those algorithms when they don't work well. This plot here shows training error and testing error as a function of the number of samples. This is a very useful graph to draw. Because what this shows is that as you increase more samples, your training and testing losses should sort of come together, right? Those should be better and better approximations of each other. But if your training loss is already too high, and by the way, this actually grows because the less data you have, the better job you can do fitting that amount of data. The more you have, sort of the less well you can fit it. But if your desired performance is down here and you're getting up here, more data will not help you. Less features won't help you because you're just making a less expressive function class. And more regression won't help you. The other things will help you, though. I'm sorry I have to be brief in this. You can go through sort of this example again. Hopefully, come to office hours and this kind of stuff. There's a question on this on the homework. It's sort of the opposite case of this, so you can think through that one. And then that, I believe, is the last of this lecture. So here's the take-home points, but you can read those. And you'll have a lot of fun doing a lot of this stuff for the homework, I imagine. So, all right.